the third and the third exercise, and after this I will do the fourth exercise of the set 6. Yeah. Okay, for this for the third exercise, as I said, the first and the second exercise, I have recorded them. I will put them today or tomorrow in Moodle. And for the third exercise, we have the pictured pendulum here, consists of a mass M and a massless rod, which has the length L. The pendulum is connected at point B here to spring with stiffness C. The pendulum moves under the influence of gravity G and is released at time t equal to 0, at the position here phi equal to 0 with the velocity v0. The given is the mass m, the length L, stiffness, and gravitational acceleration, as well as the initial velocity. As I said, the condition, the spring is unstretched for phi equal to 0, and initial condition phi at time t equal to 0 will be equal to 0. It's asked to get the differential equation of the motion with the D'Alembert principle, the eigenfrequency omega, the frequency f, as well as the period of oscillation t, under the assumption that the angle phi is small. The third question is phi depending on time, to determine phi, which time dependent at the maximum angular displacement phi max, also under the assumption that phi is small. And nota bene, here we have 2 alpha, 2 sine alpha cosine alpha, it's equal to sine 2 alpha. Okay, I go now to the solution. Then what we have here with D'Alembert, we know that the sum of the forces is equal to 0, and now what we have as forces, we introduce the what we call inertia forces, and for that I have to make the, let's say, the cut, or to determine which forces are applied on the system rod with mass m. Then what we have here, we have our rod and we have our mass here. What we have as here the point, I let the point A, here the point B, and this is here we have our angle phi. Now what we have the weight here, mg, we have the spring force here, F, I call it FFA, and we put the coordinate system. In our case, we have here the motion. It's describing, let's say, like circle. Okay. Then in this case, it's better to use the polar coordinate system. In our case, we have here A, the unit vector circumferential one, and we have here the radial AR, which is the radial unit vector. Now what we have two additional inertia forces due to the D'Alembert. Okay, as the motion it's in this direction, yeah, we have the forces here. I call it F T R phi, and I have the forces. I put it in absolute value as it's against, yeah, the direction of R. Normally should be in this direction, yeah, but I put it in absolute value that you know that it's positive in absolute value in this direction, that FTR, and here I have D'Alembert inertia force. That is means what we have here, FTR, it's here minus m, the acceleration A along radial direction, F T phi, this is will be the mass multiplied by the acceleration A phi. Okay, this two here are only, I write here D'Alembert for simplification, that you know that are the inertia forces, D'Alembert forces, then it means that what we have here, if we look to this exercise, we had it, yeah, in the lecture. That it means we use the kinematic relation to determine to get AR. It's already, yeah, given during the lecture, AR and FE, yeah, where we have here E R, it's only L phi dot square, and we have FE, the acceleration in circumferential direction. This is will be L phi dot dot. Then if we look at the mass here, the distance here or the length of the rod, it's L, okay, to the origin of the coordinate system, ARFE. Yeah, the mass has the length L, and we know that by um, relation it's only omega, yeah, cross omega cross R, and in our case R, it's only the distance L. Okay, the same here if it's only omega dot cross R, and omega dot is only phi dot dot, and R, as I said, it's only L. Also, we have here F, let's say, spring force, F, A. This is, it's always given by C multiplied by S. Okay, that's the coefficient, spring coefficient multiplied by, yeah, let's say the elongation or the compression. Now, if we define this as, okay, what we have here, we represent now, we know that it's the point B where the spring is connected. It's at the position 2L divided by 3. Okay. Now what we make here, as it's small, um, let's say angle phi, we have here, now I put, this is, we have to determine it as, we have the point A, and we have our rod here, with the mass M, and we have our point here, B. Now, if we look to the motion, let's say, like this, what we have to determine now this position S. S, when it's moved from this point, let's say I write here B, and this is B prime. That it means B is the initial point here, and B prime the actual position. Yeah, the cover distance now, this is will be S. Okay, that it means that there is the elongation of the spring with S. Now To determine this, we have the angle phi here. This is phi. Now what we do, it's only to divide this part here and make like this. This is 90 degree, yeah, the perpendicular to it. This part here, this is can be this part here can be divided into two parts. This is will be S over 2, and here S over 2. The half of S, the half of S, and we have the angle here, also phi divided by 2, and here also phi divided by 2. Then it means if we make now the geometry, we make sine, yeah, of phi over 2, as we have 90 degree here, okay? Then we have the distance here, E B prime, it's only 2L divided by 3. That it means here we have sine phi over 2 equal to S divided by 2 divided by 2L divided by 3. That is means the sine phi, it's S over 2, this distance here, yeah, divided by this distance. The same principle we use with cosine. We have cosine phi over 2. This is will be equal to R Fa divided by 2L divided by 3. Now, RFA, it's only this distance here. Sorry, one moment. This is RFA. Now, if we look this, we can get S from here, yeah, as phi is depending on time, yeah, as function, and RFA, we get it from here. That is means we get now S will be equal to 4L divided by 3 sine phi divided by 2, and R Fa, this is will be equal to 2L divided by 3 cosine phi. These are now the two let's say expression for the two variable S and R of A. Now what we do is we have to make the uh, simplification for the simplification only, but you can put it, yeah, to make the, let's say, the equilibrium in R and phi direction, yeah. Then you have to put that we will use in this case two equations, but we can use one equation where we make the sum of the moment m in point A or on the point A is equal to 0. Then it means here we get now what we have as moment. We have mg multiplied by this distance here. We have Fa, the force in the spring, yeah, multiplied by this distance, which is perpendicular. Okay, this is this distance here, yeah, RFFA. That is means we have the force FFA here, perpendicular to this RFA. Then we have here the moment correspondent, and we have also mg, yeah, multiplied by this distance here. This one is only L sine phi. And additionally, we have the inertia force, circumferential one, this one, m a phi multiplied by this distance L. Okay, this one in radial direction, yeah, make no moment as there is no distance. Okay, then this one coincides with the rod direction. Then in this case, we can write that minus mg multiplied by L sine phi. Then this is due to the weight, mg. Okay. Then we have the D'Alembert force or inertia force, m a phi. This is multiplied by L. Here, sine phi plus minus m a phi multiplied by L minus the force, spring force FFA multiplied by R F A. And this is, should be equal to 0. Then we have here Fe. It's given by this expression here, L phi dot dot. And we have also R Fa, which is given by 2L divided by 3 cosine phi. The feather, the spring force, it's divided by C multiplied by S, and S is divided by the following relation here. That is means now if I develop Further, then we will get here minus mg L sine phi minus m L square phi dot dot minus c multiplied by 4L divided by 3, 2 times L divided by 3 sine phi over 2 multiplied by cosine phi over 2. And this will be equal to 0. Then it means here if we simplify this expression, we will get here minus mg L sine phi minus m L square phi dot dot and minus 4 divided by 9 CL square sine phi. This is will be equal to 0. That means we have now we assumed and we said that we assume that to determine the differential equation, yeah, where we assume that we have here small angle phi. Small angle phi, that it means here sine phi it's equal to phi. Okay, this is the important part when it's small. Then in this case, when we develop, we will get here now phi dot dot plus g divided by L plus 4 divided by 9 C divided by M multiplied by phi. This is will be equal to 0. Now, if we look at this equation, it's in the form, yeah, this is equivalently to write, yeah, that it's phi dot dot. This is the differential equation plus omega square multiplied by phi equal to 0. Then it means from this equation we can get now that omega it's equal to square root of g divided by L plus 4 divided by 9 C divided by M. This is our omega. Okay, that is means here we have omega square. This is only this term here. That's omega. It's only the square root of this term here. Now, if we look to the, uh, it's asked here, the frequency and the period, yeah, we know that the period T, it's only defined always by 2p divided by omega. That it means here T is equal to 2p divided by square root G divided by L plus 4 divided by 9 C divided by M. This is now the period T, and the frequency F, always defined by the following relation, is only the inverse of the period. Then in this case here, this one will give the frequency F, it's square root G over L plus 4 divided by 9 C divided by M divided by 2p. These are now, yeah, the, let's say, the eigenfrequency, the frequency T, the period T, and the frequency F. Now coming to look what is the phi maximum, yeah, then we have here for the third questions, what we know, the solution of this equation, or let's say always differential equation. Here, phi t, yeah, then I write solution to differential equation here. Phi, it's always given by, this is A sine omega t plus B cosine omega t. Now what we have to do is to make the time derivative phi dot t. We derive with respect to time. A and B are constant. Yeah, this have to be determined with the initial condition. The time derivative of this, then it means we have only sine omega t, which here this term, it's time dependent. Then it means we have here the derivation A omega cosine omega t, and here minus b omega sine omega t. Now, if we look to the initial condition, what we know, that here phi at time t equal to 0, it's equal to 0. Then it means here b, if we replace now in the expression of phi, okay, we will get here b is equal to 0. Now we know also that the spring or the mass, yeah, is related with initial velocity v0, okay? Then it means here we have v always also that we know from the kinematic equation that v, it's only phi dot multiplied by L. And here we have phi dot at time t equal to 0. This is the initial condition. This is, we can write that the velocity is only v0. And here we divide by L. From the expression that phi dot at any time is only v divided by L, but at phi dot at time t equal to 0, we have the velocity here, which is only v0, as it's stated in the exercise. That it means here we get here v0 if we replace in the equation of phi dot divided by L, it's only a omega. And in this case here we get a, which is v0 divided by L omega. Then we can replace now in the expression of phi, okay? We have here phi, we replace A as B is equal to 0, that it means here phi at time t will be only v0 divided by L omega sine omega t. Okay, this is the expression of phi. Yeah, omega is already determined. Yeah. Now, if we look that for the phi max, yeah, to determine phi max, we know that the maximum can be reached when its derivative is equal to 0. That it means in this case that we have phi dot at time t should be equal to 0. Okay, this is the condition to get phi max. Then in this case, what we have here, we get phi dot, if we replace now in the expression, phi dot t, it's V0 divided by L cosine omega t. Should be equal to 0. V0 and L, are constant. In this case, we have only cosine omega t should be equal to 0. That it means here cosine omega t should be equal to 0, and means also if cosine is equal to 0, either we have sine omega t should be equal to 1. Then it means now phi max, if we replace now by sine omega t is equal to 1 in the expression of phi, then we get here phi max is only V0 divided by L multiplied by omega. Then it means here now phi max it's V0 divided by L multiplied by omega. This is the expression of phi max. Okay. I have finished with the exercise 3. Now coming to exercise 4. Now if we look to the exercise 4, one moment, only one moment, Okay. Then for the exercise 4, this exercise or this problems, this picture, you see the tutorial or the set 2, exercise 2, where we have determined already all kinematic relation. That is means the velocity, the acceleration, and so on. Then this problems here, it's only the follow of what we have done in exercise 2, set 2. Then we have an industrial robot which transport a component here with a mass m. The robot arm here can translate out of its housing and simultaneously rotate about the main axis. Given its phi, omega dot, and r, t, this all terms have been determined, as I said, in set exercise 2, set 2. In the radial direction, we have v, which is relative. Okay, here, and the acceleration, relative acceleration. What it asked for is the driving torque, MA, yeah, equivalently to the moment, the support reaction at the rotation axis of the robot, and the internal force in the robot arm here. Now, coming to this as it's a circumferential problem, now we look to the solution here. That we have here, exercise 4. That if we look now to the mass, yeah, we have here our arm, robot arm, which rotate with omega. Now we look what it happens, yeah, from above, okay? Then what we take a circumferential problem. We take this polar coordinate system with E, phi, and the radial direction E, R, okay? And here, when we cut the arm. Now we look what it happens for the mass M. We have the mass M here. What we have as acting forces on, or let's say kinematic relation before to make the acting forces, we have the acceleration relative, which is given. We have also the radial acceleration, the circumferential acceleration here, A phi. This is the two in AR direction and A phi. We have additionally that is also given phi V relative. And we have the Coriolis acceleration AC. Okay, these are the acceleration, yeah, or let's say the kinematic components which are applied on the system. A relative, V relative are given in the example as applied. The motion induce, yeah, this three acceleration, the radial one, circumferential one, and the Coriolis one. Now, if you return back to the exercise 2, okay, what we have here, we have the A relative, AR, it's only R phi dot square. We have E phi, it's R phi dot dot, and we have the Coriolis one, EC This is equal to times V relative multiplied by V dot. Okay. Additionally, A relative here is given. Now what we do? We do with D'Alembert, as we know the acceleration, AC. You have also the choice to use Newton law. If we use the D'Alembert, then in this case, what we have here, we take the robot arm, that is means we have here the connection. We take A, this is the reaction, A phi, and we have the reaction here, AR, and we have our arm, yeah, we cut here, we have here the, let's say, internal force S, okay? If we take now other direction here, and we have our mass, M, okay? We have also S in this point here, which is in equilibrium. As we cut here the robot, that it means, if I return back to the exercise, that it means here we are the contact here, the contact, yeah, to the arm robot here. The reaction is this point here, it's E, okay? Then we have Fe, let's say, which is, I'm looking from the top, okay? Fe, it's in this direction, which is perpendicular to this point here, and Er, it's in this direction, okay? Now I make the cut here, okay, somewhere here. Then we look, this is the S, which is the internal forces in the arm as we take it as a rod, okay? And we look which forces are acting on this mass M, yeah? Now, on this one, what we have the contact force N between the mass and the arm of the robot. We have now the different acceleration, or let's say inertial forces. We have in this case here M AR due to the radial acceleration. We have also M A relative. This is AR, it's in this direction, yeah. A relative also in the same direction. Then we take the inertial force opposite to the direction of the acceleration. And we have also now here the inertial force due to the Coriolis acceleration AC, and we have additionally here the inertia force due to the circumferential acceleration A phi. Then here to be clear, then we have here AR. This is the unit vector in a radial direction, and this is the unit vector in phi direction. Okay. Now, if I make the equilibrium, then we have here to write the sum of the forces in radial and circumferential um, direction. Then we get here the sum of the forces in radial direction, which is equal to 0 here. Then it means we can write directly that we have here in radial direction what we have MAR plus MA relative minus S. Okay, this is what we have in radial direction. And it means we have here MAR plus MA relative minus S equal to 0. Okay, AR, A relative are given here. This is A relative is given in the exercise. AR is given by the following relation R phi dot square. S is unknown. Okay. Then we get here from this equation S, which is equal to M multiplied by R phi dot square plus A relative. This is the expression of the, let's say, arm or rod, yeah, force. Now we take in the perpendicular direction, then it means the sum of the forces in phi direction. This is will be equal to 0. Then we have here minus M A phi plus M AC, the Coriolis one, plus N equal to 0. Okay, then we have MAC here as in the direction of E phi minus MA phi and plus N here. Then we get here from this equation the expression of N. That is only M multiplied by R phi dot minus 2 times phi relative phi dot. Now we got this one. It's asked now to determine, yeah, the driving torque, yeah, and also the support reaction. Okay, the support reaction are here AR and Fe. Okay, the support the torque here we can make now only that the moment at this point here A. Now if we look at to the equation what we have here, the sum of the forces, yeah. Now we look to the global system, yeah. To the global system, that it means we look to the here, this part here, yeah. Then it means we look completely to this part here. What we have AR plus S equal to 0, yeah. And now if we look to the support only to the forces, yeah, we have only here N, yeah, which is also N, it will be equal here, let's say, yeah, um, Fe with N in equilibrium. That is means here we get the sum of the forces equal to 0. Then we get here AR plus S is equal to 0. Then it will be here AR, it's equal to minus S, and will be equal to M minus M R phi dot square plus A relative. This is one part, yeah. Now I wrote this one to make in which direction AR, I make the sum of AR. Now to make distinction between this for the mass, yeah, M, and for the whole system now, yeah. This one now in phi direction, I make I phi equal to 0. Then what we have here, Phi is minus N is equal to 0. Then we have here Phi is equal to N and is equal to the mass multiplied by R phi dot dot minus 2 times phi relative relative multiplied by phi dot. This is the reaction in phi direction. Now, if we take for the torque, we have the sum of the moment in around the point A is equal to 0. Then what we have here, we have MA minus N multiplied by R is equal to 0. Then we get here Now MA, which is equal to M multiplied by R phi dot minus 2 times power relative phi dot. This is now the torque, okay? Now coming to the third question to determine the internal force in the robot arm, okay? Now coming to the third point, we have our robot arm here. Internal forces when we make the cut, we have the here the normal forces, I call it L as function of R. We have the Q, this is the tangential one, QR, and we have the moment MR. These are the three, yeah, in 2D, there is always the normal internal force, yeah, the tangential one, QR, and there is the moment MR, yeah. Now, what we have here, we have our point A, that it means we have here A phi, it's what we determined previously, okay. We have ER, and additionally, we have MA. This is the torque. That is means we have only to make the equilibrium, yeah. If we make the equilibrium, then we have here LR as function of R. This is will be plus AR is equal to 0. And this is we get L as function of R. This is will be minus AR. And AR we found it's only minus S. This is one part. The second one in vertical direction or phi direction, what we have the tangential internal force Q R plus E phi will be equal to 0. Then we get here QR it's only minus E phi and A phi it's only N. This is the second one. And now for the moment C, we have MR plus the torque moment MA minus E phi multiplied by R, and this is equal to 0. Then in this case here, we get, I wrote it this by to make distinction, R delta. Then we get M R. This is equal to minus N multiplied by R plus N R delta. This is now the moment M. If we look how it looks like in the diagram, okay, if we make here L, Q, and M, then if we have the point A here, and we have our arm, the same principle here, then what we get as diagram here, we get as constant here, which is positive, and the value is only, sorry, it's opposite, yeah. Then we have here, this is positive, and the value is only S, as we got it here, okay? L is constant, it's only S along the arm, yeah, of the robot. Now, if we take here the Q, this is will be negative. This is negative, and the value is N. And for the moment is linear, where we have here minus ME. And here we have minus M, and this is, it's also negative. Okay, this kind of the description of the internal forces, yeah, is the same as we have done it, or you have done it in mechanics 1. Okay, I have finished with the set 6, and as I said, I will put the Moodle, the recorded video as well